All right. I think we are golden here. I'm Justin Tolman. I work at Xtero, the forensic subject matter at matter expert at Xtero. Man, we're off to a good start, guys. We're off to a good start. But today this is kind of episode. Let me move this. I'm going to hide this. Today is kind of an episode 2, if you will, of SQLite stuff a few months ago. And I'm sure that we can provide a link or something here on Cyber Social Hub. We talked about breaking down SQLite databases. I think that was the title. And we went over some stuff like how to look at the header of the database and break down the pages and different things. And I got emails, chats, requests on LinkedIn to go over more stuff. And I was like, okay, I'll build something. We'll create something. Whatever. Time has been crazy. And then, hey, we're doing another presentation on Cyber Social Hub. So I was like, hey, let's just by request, do what, give people what they want. Okay. Looks like in chat, Megan just put the link to the first part. So, hey, Joanne, good to see you. So link is in the chat to the first part. So if you haven't watched the first part, if this was YouTube, it'd be like, pause, go watch that, come back. But it's fine. You'll be fine. We're going to do a brief review. But yeah, I just want you guys all to remember you asked for this. Okay. So we're gonna do some hex diving today, and we're gonna be in SQLite. And what we're gonna cover, what was asked for, is what I did is I showed you guys the header, and we broke down key elements of the SQLite database header, and then we just magically skipped from the header out to some content, out to, I think we looked at a text message, and we started to break that down. And one of the big questions was, how do you get from the header of the database to the actual content of a text message if the database is corrupt or whatever? And so that's what we're going to look at today, is how you would kind of do that navigation through hex. Okay. Now, one comment that I did get on LinkedIn, I think it was on LinkedIn. It may have been it's been a minute. So on one of the social platforms, either here on Cyber Social Hub or on LinkedIn, was, hey, you know, software will do this for you. Of course. Yes, absolutely. And listen, I know the forensic caseload that you guys all have. If you can get software to do this, you're absolutely going to do this. This is for 2 things. And I just want to, we went over this in the first one, but I want to remind you, this is for 2 things. One, to understand how your software is recovering SQLite database files. The second one is to just understand how SQLite works, because the more you understand, the more you know, the better prepared you are to explain it. If something goes wrong, you can hopefully work through it. And that kind of leads into the second part, is if you've ever done like a search through something and you found something that the software missed, or if you're on computer data, if it's in deleted space or something, you could work through it if the database wasn't whole, because the forensic software is going to rely on a complete database to carve it out, to parse it, to do those things. And with this, technically, you can do it on your own without other parts of the database, because you would know how to put it together and know the structure, and you could parse it out. So again, part 2 starts now. Remember, you asked for this. All right, so let's start at the beginning. We have this table. Obviously, we're going to be using a working database just for this. This is actually a database I built for a script a friend and I were making that basically sits and dumps all Twitch chat into a SQLite database. So we have the messages table here, and all the chats start dumping in as we just capture them. So we have a date column, a message column, username, channel they were on. Are they a subscriber? Are they a mod? Is this the first message they've ever put on this channel? And if they replied to anybody, and if this message was deleted. Okay. And so we have this table here. That's where we're starting. Okay. And if we look at a visual breakdown of the schema, remember the schema is the blueprint of the database, how it's laid out, how it's going to function, how it's going to work. Okay. We see the same thing here. Some other stuff that has been that's off the screen as well. You have a message GUID and all sorts of other junk. Okay. Okay. All right. That's the table we're going to be looking at today. All right. So quick review, because this will become important. At the database level, this would be the very top of the database. We have what I didn't highlight, but we have the magic header that says SQLite format 3. Okay. SQLite format 3, that kicks us off. Then we have the page size. This is insanely important to know the page size. Now, most of your apps, computer databases that you use, you're going to see 4096. It's pretty much the standard, typical cluster size, whatever. But it's important to know that if you're going to start digging through at the hex level, you need to know that the page size. And we'll use that today as we bounce around, because it influences our math on how to navigate the database. Rollback or wall right there. But we also have a page count. This is going to tell you the size of the database, how many pages that you have. Okay. This is also important, especially if for whatever reason, maybe the database is fragmented or something, you had to do a little bit more work. You could figure stuff out. But honestly, if it's getting that bad, you're going to be targeting using like live search or index searching or something in the hex to find your content, and then you'll reverse it. We kind of talked about that last time. Okay, so that's at the very top. Once you get down into the page system where the content is held, remember that's a leaf table page, B-tree page, they have a header as well. And we can see that each page will have a header type, page type. Okay. This is also called a flag. And 0D is typically where your database content will be held. Okay. So let's say real quick that you were looking for some content. You're searching through the hex, say it's computer data or some corrupted database or whatever. And you're going through, you find like a hit on, a keyword submarine or whatever, I don't know. And you could scan up from there and look for the 0D flag and then work your way back down to parse out that page. Okay. So then you have a free block that's a deleted space within the page. Cell count, how many rows, cells are rows. Just remember that. So how many rows are stored within this page? You have the cell offset area. Where does the first one start? Fragmented free bytes, and then the cells. Okay. And that's the offset within the page at where the cells, the rows start. Okay. All right. So we pick a cell. Oh, my nose itches. And we drop down into the page and we have our size of the cell. Okay. How big is the row in bytes to store all the stuff in the row? And then we have the row ID, often the primary key as well. So unique and never repeats. And so we have the row ID there as well. Okay. So we kind of move down through. Did I go too far? Nope, we're good. So then the key to determining, this is still review of the first one, the key to deciphering all this information once you're down into the cells is variable length integers. And remember, we covered in the first one, or if you weren't there, you're not going to remember. Variable length integers save space within the database by only using up the amount of bytes necessary to store the information. Okay. This is super important for SQLite because it's very concerned about how much space it takes. So we use variants or variable length integers to store that information, so that, because a variant can be up to 12 bytes long. If you had a database of 60,000 chats, well, if you had to hold 12 bytes for every single row within that database, and remember there's going to be multiple rows per chat because of contact contact information, carrier information, message information, attachment information, etc. That's a lot of bytes that are going to waste if it's not using all 12. So we use a variable length. So we're going to be doing this, but just as a review, we convert the first byte to binary, identify the most significant bit, and because these are big Indian, we're going to start at the left. So if the left most bit, the most significant bit, this is probably backwards on screen, but sorry, my left. If it's a 1, we're going to take the next byte as well. If it's a 0, we stay within that byte. We drop the most significant bit because we don't use it in our calculation. It's just there as a flag bit to tell us which bytes we need. And then we convert that to decimal. Okay. We're going to be doing this a lot, but there's the 4 steps, to converting a variant. Okay. We're going to deal with serial types today, and we covered them very briefly in part 1. Serial types are how we store columns within the row. Okay, so I'm going to come back up, which I don't do very often, but so we have a row that contains data here. Yo, what happened to Evan by Tokyo Stick Drift on channel TSM Imperial How. Okay, so we have that row. So each of these columns holds data, obviously, no duh, thank you. That's why you tuned in. And the database has to be able to track when one column starts and when it ends and when the next one starts and when it ends. And we use this with serial types. So dates we know are stored as integers. So, it's going to say, hey, this is a 6-byte integer. This is an X length text. This is a whatever, okay? And so these serial types tell the database, and then by extension tell us what type of data we will be looking at in the column set, okay, in the row, in the cell. All right. Now, just like kind of if you're familiar with the master file table, who isn't, right? Some of the data can be resident, and we will see some of that. All right. We'll see some of that as we go down through. Okay. Now we're going to do all this. So if you're like, I still don't understand what's going on, or I'm a little bit lost, that's okay, because all this is going to be applied as we go down through this database as well. But just, that's the review. All right. So the first thing that any database needs to do, we need to do if we're at the hex level, is we need to isolate the database schema. The schema is the blueprint. The schema is what tells the database what columns to have, what tables to have, how those columns and tables connect to each other as far as joins. It also tells them what to do. Like if I delete this row, does it also delete any other rows? If I delete this column, how does that impact everything? So it dictates the whole function of the database. So we need to figure that out first. The schema is stored on the first page of the database. So we have our header here. That's the page that the schema will at least start on. Okay. Most schemas for a lot of your databases, like for example, I looked at iOS SMS.db. That schema takes like 3 or 4 pages. It's so big. Okay. And in that case, right after the header, do I have a thing? Yeah. Right after the header, you would actually see a 0.5 here because it's going to have to point to some other pages as well and hold data. But what we have is, we have in this case a 0D. We will get to 0.5 pages today. I'm sure the suspense is killing you, but we're going to start with a table leaf page, which is hex 0D. Okay, because this database that I built doesn't have a ton of stuff, right? It's got a few columns, track some basic information as we pull down those chats from Twitch. Okay, but just keep in mind that you may see and will typically see 0.5, but it all functions the same, and we're gonna run through 0.5 pages later, but in this one it's a 0D. Okay, so the offset from everything here is from the start of the page, not from the start of the flag. And this is standard for all SQLite, but it's only a little weird here because we have the 100-byte header, but the offsets stay the same. Just a heads up on that. Okay, so we know now, okay, the schema is going to, this page here, this first 0D is going to be holding the schema because the database has to read that schema first to know where anything's at. So we're just going to pick this first cell. And again, if you were actually going to parse this whole thing out, you would need to go through all the different things and stack them together. That would be redundant for what we're doing today. I'm going to show you how you could do this. And again, coming back to the software comment, you would definitely want software to do this for you. But so we're going to pick this cell here, which remember is an offset 3711 from the start of the file. And we will go down to see what is connected, or what is contained, not connected, what is contained within this cell. Okay, so you found the header of the database. We started the first page to isolate the database schema. And we're going to go through each cell, but in this, we're only going to go through one cell. Okay, so now we've dropped down to offset 3711. Okay, and that puts us right here. This functions the same as what we covered in part 1 and briefly went over. We have a variable integer 8245, which indicates the size of the cell or the size of the row in the schema. And one thing I should probably talk about a little bit here, the schema's name is SQLite _master. So if you ever want to write a query to see what is in the schema, select star from SQLite master. Doesn't matter the database. All SQLite databases store their schema as SQLite _master. Okay. And that's what we're in now. So, and then it's just a standard table. So you're going to have rows, and those rows will be stored as cells. Okay. So this cell, this row, has a size of VARINT 8245. We'll convert that to 325. We'll verify or validate this again. And the row ID is 01. So this is the first row within the schema. Okay. And so if we flip over real quick, we'll go through the VARINT as a review. Okay. How did I get 325? So we take hex 82 and we convert that into binary. So 81000, 2 is 0010. Okay, standard. 45 hex is 0100, 0101. Standard stuff. What's the second step to converting a variant? We drop the most significant bit on, on this byte here. So I've highlighted it in orange. That goes away. And what we're left with is a bunch of zeros and 10. And then 10001001. We combine those two together. We don't need the leading zeros. And then we convert that to decimal, and we get a length of 325. Okay. So that's how we got that. I'm not going to do the variant for this guy because it's a 1 byte and 1 is 1 in hex. Okay. But remember the cheat here is that you can, if you know your binary, if it's 8 and above in the most significant nibble, I guess, then you know you're going to need the next one. If it's 7 and below in the most significant nibble, you know it's going to be a 1 byte variant, or that's where you're going to stop, right? So, it's quick and easy, and you can bust out just how you do. Okay, so we have this information. We just validated it. We know that this cell is 325 bytes in length, and that it has a row ID of 1. So we're in the first row of the schema. All right, so what follows the row ID is the record header. Okay, we're in a row. Now it's called the record header. Okay. We have a variant. This is a variable integer, but remember that if the most significant nibble is below 7, then we know it's 1. And so we have our record header here of hex 7. Okay. So we know that this is going to be 1, 2, 3, 4, 5, 6, 7 bytes in length. Okay. Because hex 7 is decimal 7 as well. All right. So we have the first one. I just hit, when I reach for my mouse, I hit the button, spoiler. But we know we have 7 in length. This is a variant. And you convert this, this hex into decimal to get the length of this. Now, each of these are variants as well, but we're not, I put it here as a label to remind you, but notice as we look at these, each one until here is 1 byte. Okay. So we have 17. So what are we going to do? The first thing we do with this 17 is we convert it to decimal 23. Okay. Now we look and we say, okay, 23. What do we got here? Well, it's over 13. Okay. And it's odd. So that means that the data that we're looking at is string data. Okay. Hopefully that somehow makes sense. All right. So we converted this to decimal. The resulting value, 23, we look through the serial type. It's greater than 12, of course, but it's not even. So we go down. It's greater than 13, and it's odd. Okay. So that means that the type of data it is string data or text data, and it's not resident. Okay. So how do we get the length of bytes that this data will hold? Well, it's right here. We're going to take 23 minus 13, which gives us 10, and then we're going to divide that by 2. And that gives us that our data is 5 bytes in length. So we say 1, 2, 3, 4, 5 immediately following the record header. And so we have 5 bytes. What is that? Well, if we look in the ASCII, of course, I put it down here. It's the word table. Okay, so we know that this row is going to store information about a table. Most likely this is going to contain a create statement, but you can also have other things in this column. You could have view. Okay, a view in a SQLite database can be stored in the schema. It's basically a saved select query to visualize data, so that as apps interact with it, instead of the app developer having to write scripts to do or queries to do everything each time, they can call a view, and that query is just stored within the database, and it just pulls it out. Okay, and it just exports out a thing. And so the nice thing about this forensically, just kind of going off on a tangent here, is as you look through the schema, if you see views and it's an unsupported database with your software, try those views out and see, because many of you probably in here can write some SQLite or write it really well, but this can give you a head start. You just go, oh, hey, the schema has a bunch of views, grab those queries out and run them and see what it gives you. Because a lot of times a view might be the parse database. It might be some interesting stuff like, hey, conversation statistics, that the whatever, or hey, show the, on a chat database, the little conversation preview. It might be that as well. And so you can get some information out of the view, some head starts, especially useful if, again, it's an unsupported database by whatever software you're using. The view type within the schema can give you a real head start. So anyway, especially helpful if you don't know SQLite, you can remember select star from SQLite master _master, and then just look in there for some views and then copy and paste those and rerun those queries to get you some information. All right. That's a bit of a tangent, but hopefully a helpful one. I don't know. That's up to you. Okay. So we have table. So we've taken care of hex 17. Now we go over to the next one, the next byte, hex 1D. All right. And notice that we have 2 in a row. So just to save, honestly, out of laziness, let's be honest with you. I just combined second and third columns are 1D and 1D. And again, we convert to hex, which gives us 29, which is greater than 13. It's also odd. So we run through this process. 29 minus 13 equals 16 divided by 2 gives us 8. So 1, 2, 3, 4, 5, 6, 7, 8, and an 8 again. And it's just the word messages twice. Okay, we'll take a look at why this is here in a second. Okay, but you can probably guess it's the name of the table. Cool. So we've taken care of 1D and 1D. We have 0, 1 next. Well, okay, 0, 1 is a 1 byte integer, okay, in here. And so we go out and we have 2. And 2 is 2, even though it is a variant, but we know because this is less than 7 or less than 8, 7 or below, it's just going to be 2. Okay? All right. We'll come back to why that's important here in a minute. So then we go to the next one, which this one is larger. Notice that this one is remember, they're all variants. Okay. So this guy here, 8, 4, 5D, since this is greater than 7, this is 8 or greater, we know that we're going to also need this byte as well to get the total information and size for this thing here. Okay. And yeah, anyway, so yeah, so we take this, and I think I have it right here. We have 8, 4, and so we convert that out. 5D, convert that out, and we have we drop the most significant bit and the most significant bit, and we combine it out to 605. Okay. All right. 605 is great, slightly greater than 13, and minus 13 is 592. We then divide that by 2 is 296, and we have 296 bytes in length here of the create table messages, blah, 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 blah. And you can kind of see it through here. Okay. So we just decoded our first cell, which was our first kind of table here using serial types, right? Kind of go through. Now, that's all, like, this is a lot of stuff. Remember, you asked for this. Let's kick over to here. There we go. All right. So let's validate our findings. Now, in a broken database or something where you would actually be doing this, unless you just love doing this for fun, as I sit here doing this for fun, we run select star from SQLite master, and I added a where clause. You can ignore that because I had indexes, I had views and stuff in this table. So I want to get rid of those. Where type is table. Okay. So the first column was table. Well, that's what we pulled out first as a text. Okay. What is the type? Table. And we went over that. We talked about the different stuff. Then the name of the table is messages. And notice that there's two. There's name and then there's table name, because you can have some extra formatting in there, but it also needs some code-worthy naming to just maintain stability. So you're going to get the name of the table twice in the schema. Then the root page is 2. Remember, that was that single byte, one byte integer that we pulled out as 2. And the root page, whenever you see root page in the database, that's where this table starts. Okay, that's where we're going to go next to figure out where is the data for messages held. Okay, so we parse that out, though. We're looking at it in the nice view now, but we did it in hex. Okay, and then of course the last column is the SQL, or in a table statement, typically going to be the create table stuff. So this is the code that or the query or the SQL that was used to create this table. Okay, and it doesn't look like I did anything special with this table. So we create the table messages and then open parent, and then you can dictate. In forensics, you're not going to be creating tables too often. That's more of a, you know, we don't do that. But the only thing here that I will point out is the ID, which is the primary key column, is an integer, standard thing, primary key, auto increment, and unique. If you have this auto increment, or you see, I should say, if you see this auto increment in a database, the impact that's going to have is, we'll talk about it later, is inside the record header. Following the size of the record header byte, you'll have 0, 0. And what that indicates is that the primary key is dictated by the auto increment create statement. Okay. In that it'll just always be whatever. You don't have to use that, or developers don't have to use that when they build it. Most do, because it's easy, consistent, and more stable. But we'll see that play out, how that works when we get into a thing. Okay. Okay. If you have any questions, put them in, but I'm sure, like, do we even still have people here? All right. Remember, you asked for this. This is by heavy request to go over this stuff. Okay. So what we have done now, we knew that root page was on page 2 of the database. Okay. This is a funny database because I built it and I didn't enable certain features, but page 2 is kind of a rare place for a page to start. Normally, you're going to have an index page on page 2, but here we are. So we're on page 2. How did we get to page 2? We had to know that the page size was 4096. And then what we do is we take the page number minus 1 times 496. Well, that's easy with page 2. We're just going to be on offset 496. And sure enough, here we are in a page type 5. Okay. So this is an interior page table. They're called interior. Table 5 will sometimes contain content, but more often than not, your page 5 type is just a collection of pointers, okay, telling the database where to go, okay? Because we should probably have a thing sometime on just B tree pages themselves, but it's like a lot of math and junk. But basically think of it as a tree, right? And you go to this page and it says, okay, if you're greater than 6, go this way. If you're, less than 6, go this way to this page. And it's just about splitting things off so it can find things really efficiently. Okay. And that's what page 5s typically do is, hey, go this, go here, go here, go here. And it's like choose your own adventure books back in the day if you did that. The header type, the first bytes are the same. Okay. You have the flag, you have the free blocks, you have the cell start area, the number of cells in the cell start area, then the free bytes. Okay. The thing that you do have that's new is the rightmost pointer. Okay. And this will point to the next page to the right, meaning further forward in the database. Because if you think about it visually, you have a B tree page, you have something less than this separator, okay, like I said, less than 6 or greater than 6. So you have a right page and a left page. The rightmost pointer is the furthest right page in this chain of pages. Okay, so that would be a good place to go, honestly, to check here, because we know that this is where this sort of stuff starts and we can take a look. But what we're going to do is we're going to take this first cell right here of 0 FFA and go down to 4090 on this page. And what we are looking for is these, again, are pointers to other pages that contain information about messages. And how do we know it contains information about messages? Because the schema told us that this page, page 2, was messages root page. Okay, it's first page. And in this case, it's got to be a 05 because it's got to point to all the different pages that messages content is stored on. Yeah, something like that, right? All right, well, let's look at it. So we have 0FFA, which is going to take us down to offset 4090 within page 2. Okay, so we're going to go down, and the cell format for a interior leaf page, a 05 page, is 4 bytes is the page number, and then there's a 2 byte. Oh shoot, I don't ever look at it. I'll look it up later. Maybe now if I can find it really quick. Which I can't. I'll find it by the end. I'll look it up towards the end. But it falls by a 2 byte. But what you need to know is the 4 byte page number. Okay, I can't remember what the 2 byte chaser is off the top of my head. Yeah, we'll look it up in a minute. Okay, so we've gone out to 4090. We have our 4 byte big Indian integer, which signifies the page number that we need to go to figure out to see more content. Okay. So this one says 000002B1. Okay. So the child page here, 000002B1, comes back to page 689. So we need to now go to page 689 to see what's up. Okay. So page 689 is also an interior leaf page. So it looks like our messages table is big enough that it's taking 2 interior leaf pages to contain pointers to all the stuff. And that would make sense. I can't remember how many thousands of chats I have captured, but I ran it the other day to just put some extra stuff in this database, and I was capturing an average of 500 chats a minute, and that was a slow night. So like this database, I have it on its own solid state because it blows up quick. So we're here. We do the same thing again, right? We're going to pick a cell that's going to send us to an offset within this page. Okay, we go out. Now we get, okay, now you need to go to page 00000000000F, which is page 15. All right, let's go to page 15. Okay, finally, we've got a 0D page. So maybe we're here where some content is. Why all the hopping? Well, this is how a SQLite database works. Okay, the first page, hey, here's the schema. It's going to tell all the root pages, so the database knows where each table starts within its database. And it's going, hey, I need to get something off the messages table. Okay, the root page is 2. I'm going to go to page 2. Okay, I'm going to read the first cell. Okay, I'm going to go down. Oh, I need to go to this page. And then it's going to go to this page. Oh, okay, cell, go down. Oh, I need to go to this page. Okay, I'm on page 15. Okay, I'm on content. I'm looking for this message, cell, content. Okay, and that's how it's moving down. So that's how we are moving down. Okay, just the same way as it moves down. But we know once we get to a 0D, a table leaf page, that we're going to be pretty happy, maybe, that we find some content. All right, some content. All right, so we have our header, and we can see I parsed it out kind of here, right, for your information. And I picked a not so random cell. All these have content in them, but again, I'm capturing live chats off of Twitch. So I just wanted to make sure, like, 1, it had like some good content, and 2, it was, I mean, we're all forensic people, but also safe for work-ish, you know? Anyway, which is always funny because I'm talking to a room full of forensic people, and having been one, I know what we see, but you know, presentation and all. So we're going to go to this offset 01BA 442. Okay, so we're going to go, here, and then we drop down 442 bytes. Okay, so deep breath, everyone. We're gonna go through this. So we have dropped down to offset 442 within the page. We have the size of our cell, which we parsed out to 303 bytes. We have the row ID, which with this table also corresponds to the primary key. We have 35. Okay, cool. So that stuff, forget about it. Then we have our record header. Okay, 0E indicates the size in bytes of the size of the record header. Remember, these are all variants. So, but we're gonna use our quick rule to know if the variant is smaller or 1 byte or 2 bytes. Okay, so we have 0E is our record header size. Okay, and let's go through this. All right, so 14 bytes. The next one, 00. Remember I said earlier, if this is 00, what this indicates is null, but what it's really indicating is that this row ID is what we're using for the primary key. The developers of the database used the auto increment keyword, and so it's not storing anything here. If the developer of the database did specify a primary key, you might see something here. If it's an integer, you might, or a string or something like this. And there are databases. Android old chat actually used a GUID for the primary key, and so you would actually have a different thing here. But this is going to be common. Also, we talked very briefly about recovering deleted content manually. And what happens with a free block is the first 4 bytes are going to be overwritten. And what you notice, what you lose is the size of the cell, the primary key if it's only 1 byte, and possibly the record header size. Well, that can be catastrophic, as you can see, like how to whatever. So here's some quick tips and tricks. And I know we've only got about 20 minutes less. But if you lose the first part of your record header, if right after the free block header is 00, you're in a good spot, because you can be like, okay, I'm going to look at up above and maybe down below, or maybe I know this database, it's messages, so the column order, because remember everything's going to be the same like that, and you can try to go up and down and try to match and figure out what you've got, and then from there it's how we're going to do to recover the records. So when I wrote a Python script to recover deleted messages when that happens. And that's what I did. Like, hey, if you can find this 00, blah, 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 like then build it off. It's pretty consistent. You can get pretty good hits on there. Anyway, okay. So primary key, 00. All right, expanding out our little view here. So the next one is 5, and that comes back to an integer here, and we get our date, basically stored as a big long integer, but 1, 2, 3, 4, 5, 6 byte integer. Okay. Oh, I forgot my little underline there, but whatever. Same with this one. Man, amateur hour. But what we have here is 8384. And we know with this guy, because this is 8, it's going to be 2 bytes. And this makes sense for us in this case, because this is the actual text portion of it. I didn't. Okay. But I didn't validate this variant, but we know the process now, right? Drop the most significant bit, combine it together, convert it to decimal, and we get this length of 109 bytes. And that's our message. So we just, right after the date, it just goes. Notice that there's no delimiter here. Okay. The SQLite just knows, okay, record header, null. Okay. I'm going to use this primary key. First record. All right. It's a 6 byte integer. Boom. We're just going to go through it. Okay. Got it. What's the next one? Oh, it's 109 length string. Okay. Where did I end on that date? Start there. Go. All right. There's no delimiter in the system here. Okay. Next one, length 8. I swear I had a little slider that would highlight that. I bet you I'm on the wrong slide or something. Anyway, length 8, the username. So we have 1D here, length 8, and we have, Carl Taboo or whatever. So there we go. And it again, butted up right against the thing. Then we have a length 9, okay, integer, we have this, this is probably a user ID here, okay? Put it up right against the username. You can see it over here in the text or the ASCII as well. Okay, 02, we have a length of, or 01, I mean, 1 byte integer, not resident. So we come down here, we have 02. Okay, now, now it goes back up. Jeez. 09, let's see. I don't want to go back, but let's do this. Because I want to cover this here. So 09 is an integer value of 1, and 08 is an integer value of 0. SQLite has limited data type formats compared to like legit SQL or MS SQL or whatever. There's no Boolean. There's no true false in SQLite in that you store true or false with a serial type or a data type here. So to fix that or to support that or whatever, we use 8 and 9 with integer value 0 typically meaning off or false, and 09 meaning 1 or true or on or whatever. These two values are resident to the record header, meaning that there's nothing out here in the hex that is stored relative or relevant to this data. Okay. So as we've gone through the header, we've read these values and then we've dropped down into the cell to actually get the data. Once we come to this, SQLite does not drop down into the data. It's resident. It stays up in the header. Okay. So with here, we have 09, we have on or true in this case. And then the next one is 08. Remember, we stay resident. It's off or false in this case. Same with the next one, 08, resident, off or false. And then we have 55. I swear I had a little slider up here. 55, which is the message GUID in this case, but a length of 36 type string, because it's 55 greater than 13. But that hex translates out to, 36 and everything. And we have this. And see, sometimes I do, sometimes, man, guys, lame. Then we have null, length of 4, 1, 2, 3, 4, null. And then we have one last resident byte of on or true, 1, etc. Okay. So manually, we just went through, we navigated from the header to the page, or to the schema, which told us which root page messages was on, which sent us to page 2. Okay, that's an interior leaf page. We looked at one of the cells that sent us to a page that sent us to another interior leaf page that said, okay, hey man, this table's big. It's got a lot of freaking pages. So go look at this page, which we looked at that page, which took us, we're on a 0D table leaf page. We looked at a cell, we brought it down, and now we're able to decode manually, if you wanted, all of the columns here into the thing. So if we scoot it over here, notice what we have. ID 35. That's what we had. Timestamp, that big timestamp there. The message, is it still WAF to upgrade, blah, 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 blah. Carl Taboo, 930, blah, blah, blah. Channel was 2. That was that single byte integer, right? Channel 2 is subscribed, so is on 091. He's not a mod. So 8 false. 8 false. It wasn't the first message. You have the message GUID, null, and the connection ID was in there as 09, which indicates to me that my schema is broken. There you go. I changed this thing and then don't dump the tables. So who knows what that is, but that's a problem with me, not a problem with our parsing, because we can see that this should be resident, but I must have changed something later on, which is entirely possible. but you get what I'm saying. All right. So we went from the top of the database, from the header, all the way down. Why am I doing this? To the bottom. There we go. Okay. And that's a lot of hex. That's a lot of shenanigans to get down there. And fortunately, our software, forensic software at large, whatever, does that for us. But again, if something is wrong, something isn't, the database is fragmented, it's broken, it's whatever, you can go through and you can do it in theory, right? You can go, jump, bounce through, find it, and start to bring data out. The thing that I find most applicable to my stuff is when like random pages are out there, or something's been deleted or fragmented, and I get a search hit, and I'm like, okay, this is in, you know, Windows DB or something like that. How do I put this back together? How do I just at least parse this one cell out? Okay. And do it. The other thing is you understand how the database works, right? This is how it navigates through, and you can, you know, kind of understand that. And why am I not getting the data that I think I should be getting? Well, okay, this is how the database works. Am I missing something? Is the database broken? Et cetera, et cetera. So no jury's ever going to ask you to go this deep, but you know, nerds. Yeah, great. Exactly. Thanks, Stephen. Thanks, Joanne. So any questions? I mean, we went through a lot of low level hex stuff, and we went through it very fast because we only had an hour. Feel free to hit me up on LinkedIn if you know you're just like, listen, I can't talk about this or think about this anymore, or on Cyber Social Hub, of course. This little QR code link, because here's the thing, we didn't talk anything about software or whatever, but this is if you want a free trial of FTK, you can scan that, and I personally recommend that you do it. I think we've done a lot of cool stuff with that, and we're adding a lot of cool SQLite stuff here soon this year. So anyway, yeah, I think not to set myself up for whatever, but one of the things that I personally am doing research into right now with SQLite, and I use this book, SQLite Forensics by Paul Sanderson, is overflow pages. I don't know how often, I'd be interested in chat if you guys post in there, how often do you find blob data in SQLite, like pictures or any other types of files inside of SQLite databases? If everything's working fine, it pulls out just good, but overflow pages are how SQLite stores blob data that goes past a page. And that has a whole different ball of string. What? It's a whole different world handling overflow pages. And that's kind of my next area of research. But if I get it down and get something presentation, I'll hit up Cyber Social Hub and we'll have to present on overflow pages and blob decrypting inside of databases. So yeah, I think that's where whatever. Okay. Yeah, that's it. Megan's got you in chat as a thanks. And again, hit me up on LinkedIn or Cyber Social Hub, or email me at justin.tolman@xterra.com. And or if you see me at a conference, hit me up. So yeah. Okay, regarding table relationships, aside from foreign keys, is there any good clues when looking at the table schema to see what table might be related to different tables' primary keys? Yes, there's a couple things. First off, even developers can't keep track of all the shenanigans that can connect things. So a lot of times they won't actually build foreign key relationships into the table. I'm sure you've seen this if you've dug into it, where you're like, they don't have a single foreign key like specified in the schema. Like, what is happening? Technically, you don't need it. You can force it through a query. And what you'll see is like in a table header, if I'm in messages and I have a contact table, the contact table might be called channel name. Okay. And that might be a bit small. Sorry. I wasn't planning on showing this. So, context. Channel name might indicate to you where that column is going to point to. Even if I didn't build a join statement between that and channel, you're like, okay, hey, channel name, that's where I should go look. And to kind of validate that idea, if in the schema, look at the view type view. Let me see. I can't remember if I have views in this iteration of the database. Let me see here. What am I doing? So select star from SQLite master. We'll hit play. Nope, I only have indexes, but you notice like table, index, table, table, index. If you had some views in here, that would be a good place to look. A lot of your apps and stuff will store views, and then you can see what joins they're doing and what columns they're joining on. So that's a good thing as well. Look at the column names within a SQL statement or within the tables itself, and then try to find those views, and you'll see what the developers are using to create those joins, and that'll give you a lot of good information. So, yeah. If I do like open this up within this tool. So yeah, I do have a foreign key relationship built on channel and messages here. So yeah, so channel integer references channel's ID. So, okay. Any other questions? All right. Thanks for tuning in. I know it's Hex. Part 1 is already on there. Megan linked it earlier. Check that out. Part 2 will be up. I know they will post it. Be sure to hit that up as well. And yeah, good to see you. If you're at a conference this summer, I'll probably be around. Hit me up. Have a good one. Thank you.